In this lesson, you will learn what is paper chromatography, how does paper chromatography work, how to carry out paper chromatography, and how to analyze a paper chromatogram. Previously, we have learned that filtration, distillation, and crystallizations are methods of separation. Besides these methods, we can also use paper chromatography to separate mixtures. What is paper chromatography? Have you ever gotten your homework wet before? What did you notice about the ink on the paper as the water spreads? You might find that sometimes the ink smudges and blurs, while at other times the ink may split up into colored streaks that creeps across the page depending on the type of pen used. When this happens, you are seeing chromatography in action. Here's how to pronounce chromatography. 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 Originally developed by Russian scientist Mikhail Sivet for the study of plant pigments such as chlorophyll, chromatography is a means of separating two or more components that dissolve in the same solvent. Today, it is used as an analytical technique in forensic science, pollution monitoring, pharmaceutics, and many other industries. Let's find out how this works. So how does paper chromatography work? Chromatography works on the basis of different solubilities of different substances within the mixture. So it is a measure of how well a substance can dissolve in a solvent. So, take for example, consider a black drop of ink that is actually a mixture of three different dyes: red, blue, and yellow. For this particular type of black ink, the blue dye is the most soluble in water, followed by the yellow and then the red dye. When placed in a chromatography setup with the black ink spot at the start line, the red dye will be observed near the start line, then the yellow dye in the middle of the paper, and then the blue dye near the end of the chromatography paper as the solvent moves up the paper. This separation takes place because of the different solubilities of each dye. The most soluble dye is hence found at the furthest distance from the start line. This concept can be likened to a race, where different runners of different abilities are first found at the starting position. However, when the race is ongoing, the runners separate due to their different running abilities, which affect the speed of how fast they move across the track. In this case, each runner represents a pure dye with their respective running ability representing the different solubilities. The starting position of the race represents the start line, and the track represents the filter paper.
Now that we understand the principle behind this separation technique, let's look at how we can carry out paper chromatography in the lab. On the filter paper strip, draw the start line in pencil. A pencil is used to demarcate the start line as graphite from the pencil does not dissolve in the solvent. Using a pen may cause the start line to dissolve in the solvent and travel up the filter paper, which affects the resultant chromatogram. The chromatogram is the filter paper with the separated dye spots on it, obtained at the end of the experiment. Next, put a small drop of black ink on the start line. Add a small amount of solvent into the test tube. Place the filter paper strip in a split cork and replace the cork in the mouth of the test tube. Ensure that the start line is above the solvent. If the start line is below the solvent, the black ink will dissolve directly into the solvent, resulting in no spots formed at the end of the experiment. Also, make sure the filter paper is straight. If the filter paper is slanted, the ink and solvent will move up the paper in a curve rather than in a straight line. Carefully place the test tube in the test tube rack, making sure not to shake the setup. Wait for the solvent front, which is the back moving edge of the solvent, to reach almost the end of the filter paper. Remove the filter paper from the test tube. Using a pencil, draw a line to demarcate the solvent front. Finally, let the filter paper dry, and the resultant chromatogram can be used for analysis.
Now that we have learned how to carry out paper chromatography, let's look at how we can analyze a paper chromatogram. A pure substance only produces one spot on a paper chromatogram, because it only contains one type of substance. A mixture may produce two or more spots on a paper chromatogram, because the different substances in the mixture separates out based on their different solubilities in that particular solvent. We can also identify unknown substances in a mixture using chromatography. This can be done by placing a drop of the unknown mixture together with drops of the known pure substances on the same start line on the same filter paper. To get a chromatogram, we place the filter paper with the sample and the known reference dyes in the setup as shown, using a suitable solvent. From the resultant chromatogram, we can identify a spot from the unknown mixture if it corresponds with the spot formed from the known pure substance. The same substances will have identical solubilities in the solvent, and hence move the same distance across the filter paper. RF values are obtained from the chromatogram by dividing the distance traveled by the substance over the distance traveled by the solvent. The distance traveled by the substance is then divided by the distance traveled by the solvent to derive the RF value. Identical substances will share the same RF values. Let's calculate the RF value of the pure red dye on the left. We first measure the distance traveled by the substance, which is the distance between the red spot and the start line of the chromatogram. In this example, this is 5 cm. Then, we measure the distance travelled by the solvent, which is between the solvent front and the start line. For this chromatogram, it is 12 cm. We get the RF value of the pure red dye by dividing 5 cm by 12 cm to get 0.417. To get the identity of the red spot from the sample, we measure the distance travelled by the substance. In this case, it is also 5 cm. Dividing by the distance travelled by the solvent, 12 cm, we get the same RF value of 0.417. Since this spot shares the same RF value as that of the pure red dye, we can conclude that the sample mixture contains the pure red dye.